let me just start with sort of a view of the universe that I had when I was a graduate student here, which was influenced a little bit by a person sitting here. So we live in a universe, I mean, we talked about this morning, right, that we live in a universe which is dominated by dark energy. It's, there's undergoing an accelerated expansion. You go back further back in time. There's a long period in which we were dominated by dark matter. This is sort of the period where, when small fluctuations became large under the influence of gravity, and we had structure formation, galaxies, and all of those fun stuff. Of course, we had to start with small fluctuations to begin with. And for that, we had, let me just go back one more. So for us to have small fluctuations to begin with, we've already heard about this, that we needed something early on, and we see those small fluctuations already in the CMB. Also, while I was here, I learned that a good way of generating this is to have an early period of inflation driven by possibly a scalar field. And the quantum fluctuation in this field would provide these early initial conditions. However, this period between where we see the screen of the CMB and the time inflation happened, there's a lot of stuff going on there. So let me just change this view a little bit. So here's sort of the same view, but I've changed the axes somewhat. So first, you see inflation right here on this edge. As you can see, it's at a very early time, very high energies, very high temperatures, take your pick. And that generates a fluctuation in the CMB. We've already heard a lot about this, of how this happens through inflation and all of that. And again, important part being that the universe was expanding exponentially fast, or the Hubble parameter was constant. That's why we can have this influence there. And thereafter, we know what happens from light and so on. However, there's this huge region in between, right? This huge range of energy scales from about 10 to the 14 GeV to 10 to the minus 4 GeV, where we don't really know what has happened, or at least we don't have direct observations of what was going on at that time. And this is what Dan was referring to when Roger asked this question about how low an energy scale can inflation be at. And this is sort of reflected here. Of course, after this 10 to the minus 4 GeV, Bob can tell us all about Big Bang nuclear synthesis, about light element abundance, and so on. So we have some indication of what goes on afterwards. If we take into account what we have learned from particle accelerators, particularly now the LHC and so on, we can push this boundary back. But as you can see, there's still this huge range of energy scales where we don't have a clue of what went on. I can't tell you about everything that goes on here. Okay, indeed, lots of things could have happened. Dark matter production, you could have had baryogenesis. All of these things could have happened in this period. And I'm not going to talk about all of them. I'm only going to talk about this boundary between inflation and this unknown period. And this is basically the period in which you ended inflation, and you sort of move towards this period where you're going to start populating the universe with particles, dark matter, other standard model particles, and so on. So while I go through this talk, perhaps two questions that I will try to address a little bit are the following. There's really simple questions. What did the universe look like at that time? And how did this energy transfer from the inflaton to other fields, standard model or not, how did it take place? OK. So again, you've seen this already. Dan explained this very beautifully of how, if you have a period of slow roll, that is the inflaton field is rolling slowly, the quantum fluctuations here will generate what you see in the CMB. But this period has to come to an end. Okay? We don't live in this inflationary period. And a good way to make this come to an end is just make the fields start rolling fast. Remember, a slowly rolling field is similar to an almost constant potential, which looks like a cosmological constant, so there's accelerated expansion. If you make the field roll fast, then in these simple cases, you will stop acceleration. So it's a nice way of ending inflation. Now, what happens at this period, at the end of inflation, depends strongly on the shape of the potential, as well as how it couples to other fields. So for example, if you had a really weak coupling or the decay rate was much slower than the Hubble rate, then all that would happen is this field would slosh around for a long time, and it would slowly siphon away energy from this field and would go into other particles. But this is not the only thing that happens, and indeed, Andre Linde and others have shown that a dramatically different picture can arise. So imagine you have a scalar field. Here I've just taken it as m squared phi squared as being the inflaton. You have some coupling like this. Chi is some daughter field. I'm taking it as a scalar here. If you write the equation of motion for the scalar, the inflaton field, which is going to be oscillating, acts as a mass for this field. So as this field oscillates, every time this field phi is going to 0, this chi field thinks, ooh, I'm massless, and suddenly you have a large amount of particle production every time that happens. This is a bit of a heuristic picture. It's really, the background is changing rapidly. That's what's going on, and that's what's creating particle production. So if you look at this picture on the side, let me show it again. What you're seeing is energy density surfaces drawn at about a few times the average density. So you notice that as the field starts oscillating, it fragments, and this fragmentation is happening because it quickly transfers energy to other fields, they back react, and they break up the field at that time. So in the previous case, when you were siphoning away energy very slowly, if you started out with a relatively homogeneous universe on these scales, it would remain homogeneous, whereas here it becomes turbulent and messy very quickly. Again, these nice simulations and so on, there are many codes available now that you can do this. These are just putting scalar fields on a lattice. Here's another sort of pictorial view. So you can see the inflaton oscillating, and you can see the fluctuations being created in the daughter fields. As the fluctuations become large, they back react and fragment the inflaton. By the way, I'm not going to go into detail about this, but the equations that describe it are the same as what describes a child on a swing. Okay? A child standing up and down will, if they do it at the right frequency, they will increase the arc of the swing really, really fast. It's the same equation that's describing this. So the child, up and down motion of the child can be thought of as the inflaton, whereas the arc of the swing is sort of the particle production that's taking place. There's another thing that can happen. This is something I've been involved in over the past 2 or 3 years now, which is that consider a potential which is not just a monomial potential, okay? Not just m squared phi squared or just lambda phi to the fourth, but something that usually theorists draw, right? Something that has a quadratic minimum and then flattens out. Even if the couplings to other fields are very weak, something dramatic happens in this case. So as the field is oscillating, it actually is unstable. It can't stay homogeneous. And it fragments by itself. And not only does it fragments and doesn't go into a turbulent mess that I was showing before, but it goes into these localized blobby structures. Again, what you're seeing here are overdensities. These are now factors of 10 or over the background density. And these localized structures form. These are just balls of the inflaton field. This sort of behavior is not just interesting. I, of course, was interested just because it's fun phenomenology. But it's also interesting now because Planck has told us that very steep potentials are not so good. Okay? So flatter potentials work better. So these kinds of things where the potentials are flatter seem to be the thing that Planck wants. So it's nice to investigate what happens at the end of inflation in this case. Also, there's been a lot of theoretical work, in principle from Eva, Alexander Vespal, who was here as well, Renata Kalos and Andre Linde and others, where they've constructed models where this flattening of the potentials is quite generic. By the way, if you're wondering what those blobs are doing, what the field is doing inside them, the field inside them is just oscillating, and it keeps on doing so for a very long period of time. These things, by the way, mathematically, they're called oscillons. They were around. People knew about them from the 1970s. Okay, they were given a different name historically. But these things really, there's a scalar fields, and they just live there for a long time, localized things. And as you can imagine, this is quite unusual. If I take the surface of the water and just produce a ripple, it will dissipate. Okay? Scalar fields also should just dissipate away. But there's something specific about these potentials opening up away from the minimum that makes these localized objects possible, and they will go on for thousands and thousands and thousands of their own oscillations. They were not, just to show that this is not all movies, I've done some, you can do some analytic works, and you can find out, okay, what are the conditions on the potential? It's very generic, it's opening of the potential in a very generic way allows you to have these objects, motivated a little bit by Eva's work on these DBI models where you have non-canonical kinetic terms and so on. You can also write down such conditions. Even in that case, you can write down conditions where these exist, and they're very, very generic. It's very easy to produce these things. Not just is it easy to get a potential that produces them, it's also quite generic to get them from arbitrary initial conditions. So imagine this is a one-dimensional slice. It's actually a 1 plus 1D simulation. You have a scalar field here, and it's going to be in an expanding universe. And this is relatively general initial conditions. And you see these spikes forming. Okay? So you don't have to do much to get these sort of objects being generated. At the end of inflation, you don't have these large fluctuations. You have rather smooth initial conditions, very small fluctuations. And that's OK, too, because remember I mentioned that there's an instability that sets in that generates these automatically. So you don't have to do much. And so I think it's rather, given if the inflaton self-couplings are large compared to the couplings to other fields, I think this is a rather reasonable thing that could be happening at that time. There is one condition, which is that you want the fluctuations to grow fast compared to the Hubble rate, and that's represented here. So all you want is that its potential changes shape at a scale which is small compared to the Planck scale. And this I don't think is very hard to achieve either. We've also calculated how much energy density gets locked up on these things, and it turns out more than 50% gets locked up on these things, so most of the energy density goes into these guys. That's kind of nice. And you can, based on linear theory, you can also calculate the range of parameters where this happens, and it's quite large. If you're interested, I can tell you more about this. I've been working on this, but about the stability of these objects, how long they live, what are the shapes of these objects, and so on and so forth. The quantum aspects have been explored by Mark Hertzberg, who was here as well. Okay, so just to answer this basic question, what does the universe look like at the end of inflation? We have possibilities that it could be relatively homogeneous, it could have become messy and turbulent, or it could be very blobby at that time. So quick summary of what I've just said. Slow roll ends, you have this explosive particle production, then you have back reaction and nonlinearity set in, and complicated objects can arise, including these soliton-like objects. After that, coherence of the fields in some cases breaks down, and you can just do a standard perturbative calculation to move onwards to calculate decay rates, and then reheating sets in. I have to say that I say this that you will eventually get a thermal universe, but simulations have a very hard time seeing that you get any sort of thermalization going on. So this is all well and good. Okay, I'm just doing a forward calculation. I've just shown you some ideas of what kinds of things could happen at the end of inflation. But what about observational signatures? Is there any way we could figure out what goes on at that time by looking at the sky today? And off the bat, I should say this is very, very difficult. Okay? Remember, this is happening very early on in the history of the universe, and it's not happening in an inflationary phase. In an inflationary phase, you get to take modes on small scales and move them to very large scales, which come back into the horizon. Inflation has already ended, so you don't get to take these modes and stretch them out. So that makes it difficult. Second, by BBN, we kind of know that we have a thermal universe, which makes it, it erases a lot of information. A thermal universe is a thermal universe. It erases a lot of information from that time. But there are possibilities. So after the end of inflation till Big Bang nucleosynthesis, we haven't really constrained the expansion history very well. So depending on what happens at the end of inflation, how long that period lasts, and so on, it changes the expansion history at that time. Also, although we have a thermal universe afterwards, if you generated gravitational waves at that time, those could in principle be detected. I'll say more about this. Okay. These are different from the B mode, the gravitational waves in B modes that would be measured through B modes. Those are quantum in origin. This, in some sense, is because of the classical motion of the fields. There is some sense in which, Kendrick also talked about non-Gaussianities and reheating. There's another way we could also generate non-Gaussianities from this period. There are defects and relics that could survive from this period as well. So very quickly, just expansion history. I mean, you've seen this plot before. This is a size of the universe versus a scale factor. There's inflation at the bottom, radiation, matter-dominated universe, and then cosmological constant-dominated universe. Here's a mode exiting the horizon and entering today. If you change the expansion history, you are changing what part of the potential you're probing. So the previously introduces somewhat of an uncertainty about what you are determining about your inflationary parameters. In terms of gravitational waves, just these classical motions of blobs. This is a very violent period. Generates gravitational waves. Initially, this was done by Klebnikov and Tkachev, and later on taken over recently by other groups where much stronger computational techniques were used. And people started predicting sort of what sort of spectrum of gravitational waves we expect from here. So in the vertical axis right here is the fraction of gravitational waves, a fraction of energy density in gravitational waves by logarithmic interval in frequency. On the horizontal axis is frequency. It's a huge range of scales, as you can see here. The red part is sort of what's being ruled out already. And this is just put in one sort of bin here from LIGO. There are other things, if LISA would be somewhere here, and so on. And this right here is sort of what you would expect from a signal of gravitational waves from preheating. This scale right here, pay attention to this. I mean, it could be further down. It could be here as well. And this line right here is what you would expect from CMB. Okay? Or not from CMB, but from what we know from the cosmic microwave background, what the limit should be. And if you expect a flat spectrum, that's where it would be. So these are the quantum fluctuations generated during inflation as far as gravitational perturbations are concerned. So clearly the signal is high here compared to inflation, but it's a little bit misleading because this is omega GW, and what you really want to know about is what is the typical strain in the detector. And the typical strain in the detector actually scales inversely. It goes as the square root of the fraction of gravitational waves, but goes inversely with the frequency. So the higher the frequency you go to, it becomes harder and harder to get these detected. This scale right here, as I said, depends basically on the scale of inflation. So if inflation is low scale, you move to this side, and it makes it more easily detectable. So if Planck doesn't detect gravitational waves, the future experiments don't detect gravitational waves, it makes this better. It moves this way, and more in the detectable regime. But of course, right now, we have no constraint, and this is quite wide. Like it could be anywhere here. So if you would detect this gravitational wave background, you would also say something about what was the energy scale at the end of inflation. By the way, this is something, if you just want to know typically what is the amplitude of this gravitational waves in terms of the energy fraction, it's not a very difficult calculation, although maybe you wouldn't have trusted it if you didn't already have simulations. So it's a product of three factors. The fact that the universe was not radiation dominated, is not radiation dominated today. There's a factor here which basically says how anisotropic things were. This is basically, you need anisotropic stress to generate gravitational waves, and how relativistic things were. And if you put these together, you get a factor of 10 to the minus 10 to 10 to the minus 12. And basically, all calculations that done in detail will also show that they lie in this regime. As I mentioned before, there's also, and Kendrick mentions a little bit as well, that there's reheating can also generate non-Gaussianities. There's this nice idea recently initially started with Chambers and Rajanti, and then a correct calculation done by Bond et al. Recently, where you have the type of the reheating or what happens depends strongly on the value of some light field that's present during inflation. And it's so sensitive that from one patch to the other, you can have dramatically different results. So different Hubble patches expand quite differently, and this generates some non-Gaussianity. So reheating sort of acts as a nonlinear amplifier, if you want. There's also, again, there are strong people in both camps about whether you could use the Higgs as an inflaton. It would be nice for reheating because the couplings would be known. But it's not so good because you really need what is called a large non-minimal coupling. That is, you have to couple the scalar to the scalar of the inflaton directly to the Ricci scalar. And you need a rather large one. And it's really in the energy range where we haven't really tested the Higgs potential. Right? So can we trust it, or are we just inventing a potential to get this done? Right? Okay, so in the last few minutes, let me take sort of a tangential view, because you've seen all this nonlinear stuff. And I personally enjoy this field also just because they're nonlinear dynamics, and I enjoy nonlinear dynamics in general. And these nonlinear dynamics that we study at this time, they have influence not only on sort of problems in the contemporary universe, but I've also used some things that we learned from lasers and so on to attack problems there. So I want to say a little bit about this. So here's sort of an example of a problem. So you saw all these blobs created, and we did some stability analysis on this. And it turns out that the stability of these blobs is the same, mathematically it's exactly the same as what is needed to study the stability of laser beams as they propagate through a saturated medium. So based on that analysis, we made a curve of the width versus the height of these blobs. And then we took what we got from simulations and plotted them on there. The dashed line is what we predict for the stability region. And it was quite nice to see that everything that ends up is in the stable region and it goes away. So this is nice interplay between what we learned from these lasers and we could apply it here to just understand the stability of these objects. Another thing which I'm excited about currently, this again was motivated by what I was doing about trying to understand the interaction of these blobs very early on. But I think, honestly, I should say that it's more a mathematical problem than actually solving something at that time, which is trying to study the interaction of these things. And if you think of these things as sort of solitary waves or soliton-like objects, it's usually a very hard nonlinear problem to study interactions. You can write down solutions for individual guys, but it's very hard to study the interactions. Just to give you an idea of the kinds of things that can happen, take a look at the top part. Okay? And here is a collision of two of these guys at relatively low velocities, not too high. And it's very complicated. You don't think you'll have any analytic handle on this. Now the same system I'm showing you again, but now the collision is happening at very high velocities, and suddenly the interaction becomes extremely simple. So you have some hope that if these collisions are happening at high velocities, you'll be able to get a handle on these things analytically. So we did this. So we took one soliton and basically threw a very energetic soliton at it, meaning a very fast-moving one. The fast-moving one, if it's scalar field theory, it will be Lorentz contracted. And then it'll generate some perturbation, and we want to calculate what the perturbations are. If you take a view from the top of this structure, you'll find that the area of overlap between these two, which is shown right here, so here is space, time, here are the two guys going through. This area of overlap will be suppressed by gamma v, where gamma is the boost factor of the incoming guy, and v is the velocity. And as gamma goes to infinity, this interaction area goes to 0, and you can imagine that the perturbations generated by that will also be small. So this is why at high velocity collisions, you see almost no perturbations generated, and it's very simple. So we took this idea a bit further, did a perturbation expansion in 1 over gamma v, calculated things. Here is an example of a calculation. This is a type of soliton called a kink. You'll see a collision between two. You see the black is what you get from just the superposition of solutions. The orange is what you get by a full calculation. We want to analytically estimate what this difference is. And after some work, based on what I just told you before, you can calculate what it is. And it turns out to be this really nice, simple formula right here. It's a highly nonlinear problem, but you can still write down the answer here. These phi1 and phi2 are just dummy variables, and v is just a potential in the Lagrangian. So if just somebody goes to your Lagrangian, you can calculate this. Okay? You don't have to even solve the background equation of motion, which is quite nice. And it's valid for integrable and non-integrable systems. It's independent of kink or kink anti-kink. And it works at high gamma limits precisely where simulations are extremely difficult. High gamma means things get very sharp. It's very hard to do simulations there. And this is precisely the regime that it works well. We tested this numerically. It works quite well, as you can see with the curve versus the data points right here, the dots from the simulations. The potentials are arbitrarily far from integrable, and it works quite well. This is sine Gordon. We also get negative phase shifts. Again, not to worry about at the moment. OK, so that was sort of end of the tangential part. Okay. All right, so coming back to this original question of reheating and this populating the universe. Okay, so what is the way forward for this? So on the theory side of things, I think it would be really nice for me as a phenomenologist who works on trying to understand what the implications are, what kinds of things that can happen in this nonlinear regime. I'd like to know not just what the inflaton potential is, but also something about what kinds of couplings should I expect. Okay, so it would be nice to have models that not just give me a potential for the inflaton, but also tell me something of what's happening at the bottom of the potential. Are there connections, when you write these things down, are there connections to other processes that happen at that time, baryogenesis and so on? I just was talking to Mark Hertzberg and Joanna Karoubi at MIT, and they're writing a paper on where they have an inflaton being a complex scalar field, and there's a connection with sort of the particle number associated with that, and baryon, and you know, the eta 10 to the minus 10 would be the photon to baryon to photon ratio. So it'd be nice to have more of these connections coming about. As far as phenomenology is concerned, I've talked a little bit about this already. You know, nonlinear analysis, of course, I enjoy that. It's fun on the whole. And the numerical part has also come along a long way. There are fun offshoots that happen during this period, which are fun to explore. As far as observations are concerned, I think high-frequency gravitational waves, these are hard to measure. There are no experimental probes right now of these really high-frequency gravitational waves. There are some ideas that are floating around. There's Michael Cruz at Birmingham who's thinking about going to this really high-frequency regime. And in a very simplistic way, the idea is that you have a gravitational wave coming in. You have a strong magnetic field. It shakes up the magnetic field. It generates a little bit, a photon or a small amount of electromagnetic radiation, and you build a really sensitive instrument to detect that. This is hard. The sensitivity, I mean, this is basically you know, it's a small lab that they've tried to show that this can be done, but it's nowhere close to the sensitivities. Okay. The strain, the typical strain that you want to measure for these preheating-like things, for example, if you're trying to measure something like a megahertz frequency, you need to measure strains of order 10 to the minus 30. Remember, LIGO is going to go at 10 to the minus 23. Okay, so it's far away, but remember, these waves that you're talking about are not so long wavelengths, so small-scale experiments can detect this. And electromagnetic things we can do much better. So it would be nice to think a little bit more in this direction, whether there are things we can do on small scales to detect these things. There is not much happening at these high frequencies, as far as I know, from the astrophysics side. Okay. So it'd be nice if we could see a signal from this very early universe. And it'd be nice if more efforts were there observationally to try to detect this. I've talked a little bit more about the other things that can happen. I don't want to go into this in detail. Okay. So just before I summarize, remember we started, there's a huge range in energies where we don't know what's going on in the universe. I've just told you a little bit about the kinds of things that can happen at this very early stage. There's a lot that's unknown. And so I'll end with my summary here. I wanted to point out a bunch of undergraduate students who have worked on this stuff, and in particular, Michael Pierce, who was at MIT and is now at Stanford. Fantastic, fantastic student.
Questions? Over there.
Thanks, Mustafa. I always have this issue at the moment. I'm sort of thinking through for scalar fields, right? I mean, they partially behave like dust. And I'm trying to wrap my head around how this works in your case now. Because if I have a dust solution, it would sort of wind up as it does these oscillations. And I get I don't get a sort of a wave solution to that. And so can you sort of, I mean, is there sort of an easy hand-wavy picture you have that what sort of stabilizes your?
Okay. So when we're thinking of pure dust, the simplest connection is just to m squared, phi squared sort of models, right? There is no nonlinearity in the potential. And things are just oscillating at the bottom. And at the background level, it just, the equation of state is 0 when you average over many oscillations. And even when you look at fluctuations, you can show that whether you treat them as a scalar field oscillating or whether you treat them as a fluid that looks like zero pressure fluid, they both give you the same answer. There are small scales where they're different from each other, especially when the wavelength, if you're looking at so without expansion, if you start looking at wavelengths comparable to the mass of the scalar field, then clearly it behaves more like a wave than a particle, and then you can't trust it. Okay? But beyond that, it behaves the same. Here something is different, which is that it's a nonlinear, it's not just m squared phi squared, there's a lambda phi 4 term as well. And that changes things. So these objects are much wider than just m inverse. And what's stabilizing them is not any specific parameter in the problem, but it's really the shape of these objects. So think about it this way, that you have a...
I understand this also for solitons that we have in hydrodynamics, but what I'm thinking about here is because you have gravity, you always build up a phase shift normally, and it's sort of hard to keep the shapes. That's what keeps confusing me.
So no, but I'm saying that here the shape is maintained because you can't radiate away things. Mm-hmm. You basically have a shape, it's an antenna which wants to radiate at a frequency of m, whereas your shape is much wider and you just can't dissipate. So it stays at it as it is. If you include gravity, I don't think that part will change significantly at all.
Thanks.
All right, well, we're running a little over, so I think we'll probably cut it off there. Thanks to all the speakers at this session again.